there.
Hello, Mindsetters. Welcome to it. It is a Monday and it's Maths for Grade 12s at 6 o'clock. I am Luni and joining me in studio is Lisa. How are you?
The two L's tonight.
Yes.
I'm very well. I'm very well, and I'm really looking forward to this lesson on exponential and log graphs, inverses, and so forth.
All right, guys. So she told you what we're doing. So Lisa, I'll send you to your board while I tell the Mindsetters what you need to know for the show. So guys, you can contact me on Facebook at facebook.com/learnextra. You can also hit me up on Twitter. It's been very quiet lately. So guys, please talk to me on Twitter at learnextra. You guys can download all your show notes at learnextra.co.za/live. All your videos, all your schedules will be there on that page. And guys, I'll be telling you about future stars later on. Don't forget, it is Earth Day, so I hope you guys are doing good for the Earth. And you guys are not polluting anything, and you guys are doing great stuff, you know. But anyway, guys, I hope you're ready for the show because we're about to kickstart with Lisa. So Lisa, take it away.
Right, guys, so we're going to start the show by just quickly revising your basic exponential graphs from grade 11, because the inverse of these exponential graphs are log graphs. So if you don't know what the exponential graphs look like, you're going to have a bit of trouble with the log graphs. So before we have a look at the exponential graphs itself, I think it's very important that we just talk about some terminology. Now, the first thing that I want to talk about today is, what is a function? A function is a mathematical rule that maps an input value to a unique output value. Now, guys, we have dealt with functions before. Exponential functions, exponential graphs are functions, hyperbolas are functions, parabolas are functions, straight line graphs are functions. So basically, a function is a rule that maps an input value to a unique output value. Now, one quick way to check whether you are dealing with a function is to use something called the vertical line test. Now, let me bring up any graph. Let's do a parabola. Right, so I've got a parabola over there. Now, I know that a parabola is a function, but if you want to test using the vertical line test, what you will do is move your ruler in such a way that at any given time you are parallel to the y-axis. So let's just do that. So at any given time you're parallel to the y-axis, and what needs to happen in order for this graph to be a function is that your ruler can only cut your graph once at any given time. What do I mean by that? Well, if you have a look at this graph over here, let's bring up a ruler. Can you guys see that? And my line won't work, isn't that lovely? Can you guys see that here the vertical line test is not passed, because that vertical line cuts our graph in more than one place. So the easiest way to check whether we are dealing with a function is the vertical line test, and at any given place when I draw a line, I'm only allowed to intersect once. Right, so here are the notes, and if you downloaded the notes, you'll have them. We use a ruler to perform the vertical line test on a graph to see whether it's a function or not. Hold a clear plastic ruler parallel to the y-axis, in other words, vertical. Move it from left to right over the axis. If the ruler only ever cuts the curve in one place throughout the movement from left to right, then the graph is a function. Right, so that's very, very important. Right, some other things that we need to talk about are domain and range. Now, guys, by the time you get to grade 12, you should really know what domain and range are, because you've been doing this since grade 10. Now, domain is the input or the x values. So domain is what is happening here. What x values is my graph defined for? Whereas the range is the y values. So to give you guys a quick example, let's say I have again a parabola, and I tell you that that parabola has a maximum turning point at x is 1 and y is 4. If I now ask you for the domain and the range of that parabola, you need to investigate. Now let's look at the x values. Is there any restriction at all on the x values of this graph? No. It will carry on forever and ever and ever to positive infinity and negative infinity. So we can say that the domain is x an element of the real numbers. Alternatively, you can use this notation where you say x is an element of negative infinity to infinity. And remember that the infinity signs are always accompanied by round brackets. Now, if we look at the range of this graph, we look at the y values that this graph is drawn for. So the highest y value that this graph ever gets to is over here at 4. So it goes from negative infinity up towards 4, but then it starts going down again. So when I talk about the range of this graph, I will say y an element of negative infinity all the way up to 4, or alternatively I can say y, and actually it's included at 4, sorry, so that needs to be a square bracket because my graph is drawn at 4, or I could say y is less than or equal to 4. These two notations are equivalent. So usually, guys, you'll have the sketch in front of you. You need to ask yourself just some simple questions. What's happening with the x's and what's happening with the y's? Right, so that is our domain and range. We've spoken about the vertical line test. Now, before we carry on, I just quickly need to talk to you guys about your basic exponential graphs. Right. So the general equation of an exponential graph is y is equal to ab to the power x plus p plus q. Now, guys, most of the time our graphs won't actually be that intricate, but what does the q do? The q facilitates the up and down shift of my graph, and the p facilitates the left to right shift of my graph, and then the a governs the steepness. Right, so how quickly does it go uphill? Now I'm going to start by drawing a very basic exponential graph. Y is equal to 2 to the power x. Now guys, I would recommend that you know all the properties for these basic graphs, because everything else you will deduce from your basic graph. Now you can use, on your calculator, you can use your table function if you're not sure of what that graph looks like. In case you guys don't know how to use that, mode, and I'm going to go 3 for table, and then I'm going to say f of x is equal to 2 to the power and alpha x. So there I've put in f of x is 2 to the power x. Now, guys, you should know what your graphs look like, but if you're unsure, then this is one way to deal with it. And then it's going to ask you, where do you want to start? Now, when they ask about the start, we are talking about our input values or our x values. So let's start at -4. And where do we want to end? I think 5 is sufficient. And we're going to go up in steps of 1. Then what your calculator is going to do for you, it's going to give you your input or your x values, which will be your domain, and it's also going to give you the corresponding output or y values, which is your range. Now let's have a look here quickly. At -4, the y value is very, very small. At -3, it's also small, but it's getting bigger. And as I carry on, I can see that at x is -1, y is 1/2. At x is 0, y is 1. And what then starts happening is the graph increases very rapidly. So we need to know, for a graph in the form y is equal to a to the power x, as long as a, now that's in this case my 2, is bigger than 1. So let's just write there, A is bigger than 1. What your graph is going to look like is like this. It's going to get very, very close to the x-axis, and then it's going to increase quite rapidly. That's the basic curve that we're looking at. That y-intercept over here is at x is 0, y is 1. Now, in the case of this basic graph, you have got a horizontal asymptote, and that is your x-axis. And the reason for that is we can see this as y is equal to 2 to the power x plus 0. If I were to now do y is equal to 2 to the power x plus 1, that will vertically shift my graph up by 1 unit. So instead of my asymptote being the x-axis or the line y is equal to 0, it will now be y is equal to 1, and everything else will shift from there. So it's very important that we know what our basic graph looks like. Now, if I have a look at y is equal to 2 to the power x, I can see that the domain, the x values, is xer. There's no restriction on the x values. And the y values, or the range, is from the horizontal asymptote upwards. And now in this case, it will be from 0 to infinity. So that is our very, very basic exponential graphs. I'm going to do the other one as well, so I'm just going to make a quick summary. We'll say this is y is a to the x, where a is greater than 1. There's my y-intercept at 1, and my domain is x, an element of the real numbers. And my range is y greater than, I'm going to put HA for horizontal asymptote, but in this case it's 0. Right, then we can also draw a graph, y is a to the power x, where a is not bigger than 1, where a is greater than 0, but less than 1. So that would be something like y is a half to the power x. Now the graph y is a half to the power x is exactly the other way around from its friend over here. They are reflections in the y-axis. So the graph y is a to the x, where a is bigger than 1, is increasing. So as I look from left to right, the graph gets bigger and bigger and bigger. This one is decreasing, so it's exactly the other way around. But again, the domain is x, an element of the real numbers, and y is greater than the horizontal asymptote. And in this case, the horizontal asymptote is at 0. All right. So these are the basic properties of the exponential graphs that you have to know. Now, I'm going to talk to you guys about what is an inverse. Now, in particular, the inverse of exponential graphs get asked a lot, but you can get the inverse of any graph. So let's have a look. It says here, an inverse is a function. An inverse of a function is a mapping of all the output values to the input values. So basically what we're saying is we are reflecting our graph in the line y is equal to x. So that the original function has a certain set of x and y values. For the inverse, what we do is we swap the x and the y values around. And for that reason, my graph is your function and its inverse will always have symmetry in the line y is equal to x. Now, let's have a look at the first graph that we drew. I'm going to draw y is equal to 2 to the power x on here. Right, so that's y is equal to 2 to the power x. Now, the inverse of y is equal to 2 to the power x is a graph such that if I were to draw this in a very wet koki and fold on that line y is equal to x, that would be the resulting graph. So, without knowing even what it looks like yet, or without knowing the notation even, the graph will look something like this, so that if I fold onto that line, if I fold onto that line, the two graphs will be on top of each other. All right. So just quickly, before we carry on any further, what happens when I do an inverse? Let me start with given f, where f is the graph, y is 2x plus 1. Okay, so this is my function, my original function. Now I'm going to have a look at the inverse of this function. Now, what did I say just now? I said an inverse is a reflection in the line y is equal to x. So actually what happens is x and y trade places. So instead of having y as 2x plus 1, the inverse will be x is 2y plus 1. And can you guys see that they have traded places? My x is now where the y was, and using another color, the y and the x have also switched around. Now, usually, it is considered more elegant to write our graph in the form y equals. So what I'm going to do here, I'm just going to make y the subject of the equation yet again, and this is going to give me y is equal to a half x minus a half. And if you were to draw this graph and this graph, you will see that they are symmetrical in the line of y is equal to x. Well, it's already time for our first break. I feel like I've been talking non-stop. Looney, what's happening on the page? Are people following?
Yes, everyone's enjoying it. Everyone's tuned in, so yeah.
Fantastic, guys. We're going to give you a quick break, and then we'll be right back here. And we're going to start looking at some actual exam-type questions on functions and inverses.
Yes, guys, we are going to take a very short break. I'd just like to let you know about the Future Stars competition. Enter that, guys. There are so many prizes to win. The information is on our Facebook page, so if you just go through that, see what you need to do, ask your friends to vote for you, and then just click on it and look through it and just, yeah. Guys, I also like to remind you that it is Earth Day, so just be safe, keep this earth cool, don't waste water, don't waste electricity, all of that, Mother Earth is a great place to live in. We don't want to live anywhere else, guys, so do take care of it. We're going to take a very short break, so do stay tuned, and we'll be back after this. We're back, guys. I hope you're refreshed. I hope you got some water and some juice and you're ready to continue with the lesson. So I won't waste any time and I'll take it back to my beautiful teacher.
All right. Well, thank you for that. Okay, guys. So we've established now that to get an inverse, what we do is we swap the x and the y around. Now, I want us to go back to our basic exponential graph. Let's talk about y is 2 to the power x. Right. So we've said earlier on, we know what this is the line y is equal to x. We know what this graph looks like. It increases very steeply from left to right, like so. Okay. And we also know that the graph y is equal to x, or the function y is equal to x, its domain is x an element of the real numbers, in other words, all x's, and y greater than 0. Okay, now, let's talk about the inverse of this graph. I've shown it to you guys before. We said that the inverse will be a reflection in the line y is equal to x. Now, just now when I was dealing with the straight line graph and its inverse, what I did to get the inverse is I swapped the x and the y values around, and then I made y the subject of the equation yet again. Now have a look what happens when I do that over here. Instead of y is equal to 2 to the power x, I'm going to write x is 2 to the power y. All right, that's fine. So we know that the equation of this graph is x is 2 to the power y. However, guys, it's not conventional for us to write our answer, our equation as x equals. We always have to write it as y equals. And it is because of this little tricky situation over here that log notation was invented. Now, there's a process involved in making y the subject of the equation. You don't have to ever show this, but I'm going to quickly go through it. Basically, what we'll do is we'll insert a log on either side. Then we will use the log law that says if I've got log of b to the power a, I can write it as a log b. So basically, that allows me to bring that y in front. So what I'm going to have here is I'm going to have y log 2 is equal to log x, and then dividing both sides by log 2, I get y is log to the base 2 of x. Now, if we have a look here, it's actually very easy. If you have as your original graph, your original function y is equal to 2 to the power x, its inverse will be y is log to the base 2 of x. So you can just learn that. Whatever now appears over here will appear over here. And the reason why the log notation was invented is so that we can make y the subject of the equation. Guys, let's just quickly have a look. I've spoken about the domain and the range of my exponential graph, the purple one. Now let's have a look at the domain and range of my log graph. What has now happened here is for the domain, do you guys see that this graph is not defined for negative x values? It stops right here at the y-axis. So the domain is x is greater than 0. However, the range, it can go up for as long as it wants to and down for as long as it wants to, is y-er. Now, what I want you guys to notice is that my original graph's domain becomes the range of the inverse, because what happens with inverses, the x and the y values switch around. So that's really, really important. Just a couple of things. If I look at the graph y is 2 to the power x, it's very definite that y is equal to 2 to the power x. Just the purple graph on its own is a function, and the reason for that is because it passes the vertical line test. Its inverse is also a function because the inverse passes the vertical line test as well. Right, we're going to have a look at some point later on at when the inverse of a function is not a function, but that's more stuff for next week. Right. So now just to consolidate whether you guys know what's going on, whether you can do your basic graphs, we're going to move on to the questions that I've selected for us today. These questions all come from past papers, so if you can do them, you can feel quite confident that you know more or less what's going on. So let's look at those questions. Okay, on your notes, if you've downloaded them like you should, you will get some notes on the log and the exponential function, which I have explained just now. Okay. Our first question says, given that f of x is equal to 1/3 to the power x, determine f to the minus 1, writing your answer in this form. So whenever we see that notation, f minus 1, we are looking for the inverse. Now, this particular question doesn't require us to do a sketch, but because we're still getting used to what everything looks like, I'm going to start out, before I even bother answering the first question, by just drawing a rough sketch of f of x is 1/3 to the power x. And this you should know from the properties of the graphs that I discussed just now. Remember I said, for a graph in the form y is equal to a to the power x, if a is greater than 1, your graph will be increasing from left to right, looking something like that. For a graph in the form y is a to the power x, if a is greater than 0 but less than 1, in other words, a fraction, like what I've got here, y is equal to a third to the power x, then that graph will be a reflection in the y-axis of the other graph. So this graph that I'm looking at is going to be decreasing. Right? And I know that the y-intercept is where x is equal to 0, and for a third to the power 0 is 1. So that's basically what my graph looks like. Okay. So that wasn't required, but I'm just doing that so that you guys can follow what's going on. The first question I'm asked is to give the inverse. Now, I've started with an exponential graph. Its inverse will be a log graph. Fine. So if my exponential graph is a third to the power x, then its inverse is going to be, and we'll write it over here, y is equal to log to the base a third of x. Right? Take careful notice. My general formula is if I've got y as a to the x, its inverse will be y is equal to log to the base a of x. So have a look at the place swapping there. Right. Next question deals with the domain and the range of my inverse graph. Now, you don't actually have to draw the inverse graph to know the domain and range, because you know that the domain and the range will swap around. What do I mean by that? These two graphs are symmetrical in the line y is equal to x. So if my original graph f had a domain xer, then my inverse will have a range of y, an element of the real numbers. I've drawn it in purple, but you don't actually even need to draw it. You can just know that from the properties of the original graph. And then again, if my original graph had a range of y is greater than 0, then the domain of my inverse graph will be x is greater than 0. So, yes, I've drawn it to show you guys, but it's very important that you know the domain and range of your basic exponential graphs, because you know for the inverse, they just swap around. Looney, how's the page looking?
No, people seem to be enjoying the show, so... No
Wonderful,
question.
100% then. So let's get on with the rest of the questions. Right, so question C says, give the equation of the line about which f and f minus 1, its inverse, are symmetric. Now, guys, we've spoken about this at length. Any inverse, and it needn't be a log and an exponential graph, are symmetrical in the line y is equal to x. So if we have a look earlier on when I was still drawing nicer pictures, exponential graph, log graph, and the symmetry most definitely lies in the line y is equal to x. And that's not just true for log and exponential graphs. Log and exponential graphs are inverses of each other, but for any graph, a straight line and its inverse, a parabola and its inverse, the symmetry will be in that line y is equal to x. So if you were to fold the page on the line y is equal to x, then the two graphs will fit onto each other perfectly. Right, let's have a look at the rest of this question. Let's just get there. Right. The final question says, determine G, the reflection of f in the y-axis. Okay, so let's have a look. F is my original graph, and that was a third to the power x. Now, in our lesson last week, we spoke about reflections, and we said that if we're reflecting in the y-axis, what happens? the x value becomes negative. And remember, you don't have to commit this to memory. Make yourself a little point. Say, x is 1, y is 3. I now want to reflect in the y-axis, that's over here, minus 1 and 3 will give me that reflected point. In other words, the y value stays the same, but the x value changes its sign. So, for the reflection in the y-axis, I will say f of x is a third, and because the x value becomes negative, negative x. Okay. Guys, one thing at this point which I think is really important, and a lot of students don't always realize this, is I've been talking about a third to the power x for this question now. There was a bracket over there, that's a third to the power x. Please note that instead of a third, I could write 3 to the minus 1, all of that to the power x. So in other words, 3 to the minus x. So please notice that a third to the power x and 3 to the power negative x is in fact the same thing. But anyway, so the equation of the graph reflected in the y-axis is f of x equal to a third to the power minus x. Now this too I can simplify. I can say 3 to the minus 1, everything to the power minus x. So I get 3 to the power x. And guys, very early on in this program, I showed that to you guys. I said that this is my increasing graph. That was 2 to the power x. Now, its reflection in the y-axis will be a half to the power x or 2 to the power negative x. So I hope that you guys are following. The main thing for me is with most of these sorts of questions, after a while they do all start looking the same. So it is really important that you get enough practice. Now let's just have a quick look at what our next question is about. Right, so in our next question, we've modeled part of the FIFA World Cup logo onto an exponential graph. You guys will remember, well, if you look back now at papers from 2010, you'll see everything is themed around soccer. So what we have here is an exponential graph in the form f of x equal to a to the power x. This graph's domain is restricted. So this graph is only drawn from x is minus 2 to x is 3. So let's say it finishes there at x is 3 and it starts here at x is minus 2. It's fine. Usually an exponential graph's domain will be xer, but we can restrict the domain. That's not a problem. Right. We are also told that 2 and 4 is a point on our curve, and then we are asked various different questions. So I think, Looney, what we're going to do is we're going to take a bit of a break while our students think about this question, and then we'll be back and answering it.
Okay. Guys, as Hazel said, just think about it for a few seconds, and we're going to take a short break. I'd also like to remind you guys that if you have any questions and we don't get to them, you can write your question to helpdesk@learnextra.co.za, and a teacher will answer you guys within like 48 hours. So don't sweat it. If you have a question and we don't get to it during the show, just go to that website and type your question in there, and then you'll get help. Don't forget to hit me up on Twitter @LearnExtra, on Facebook at facebook.com/LearnExtra, and you can download all your show notes, the videos, the schedules on learnextra.co.za/live. Right now, though, we are going to take a very short break, so do stay tuned. We're back, guys. I hope you're refreshed. I hope you're ready to carry on with the questions. I hope you thought about the question and that you're ready to start again. So, Lisa, take it away.
Right, guys. So before the break, we said we had an exponential graph modeled on the FIFA World Cup, and it is f of x equal to a to the power x. My domain is restricted from and including minus 2 to and including 3. but we'll deal with that in a minute. The first question asks us to find the value of A. Now, it is very important to have some sort of an idea of what you're working towards. Now, I can see that my graph is increasing. And I know that my exponential graph is only increasing if A is bigger than 1. So that at least gives me some sort of an idea of what I'm working towards, and I'll at least know if I made a bit of a mess up. So I'm going to start by saying y is equal to a to the power x. Then I need a point on the graph, which I do have. X is 2 and y is 4, to substitute in here. So I'm going to say 4 is equal to a to the power 2. So if a squared is 4, then a must be 2. So very, very simple calculation. You write down your defining equation. They gave it to us. And you need one point, x value and a y value, an ordered pair that lies on the graph, and you can substitute in to find a. So pretty straightforward. Right. Now, let's have a look at the next question, and this is where you guys will start seeing how things form a pattern. Now they say, find the equation of g, where g is a reflection about the line y is equal to x. So what are they asking us for? They are asking us for the inverse. Right. So at this point, we should know that if we start with a to the power x, our inverse is y is equal to log to the base a of x. Right. So I've shown you guys what we do to get from the one form to the other. We basically swap the x and the y value around, and then we do a little log manipulation, but it's perfectly sufficient for you to now just use this fact that I've written down here for you. So therefore, if my original graph is y is 2 to the power x, its inverse, g, will be log to the base 2 of x. Right, so I've just applied this little rule. Okay. Now they start asking us about the domain of my inverse graph. So let's go back to our original graph. For my original graph, the domain, because it was restricted by the question, the domain was x an element of -2 up to and including 3. That was my domain. And for my original graph, the range was y greater than 0. Right. Now, remember that my domain and my range now swap around because the two graphs are inverses of each other. X becomes y and y becomes x. So, if I now look at the domain of my original graph, that will now be the range, if I look at the range of my original graph, that will be the domain of my inverse. So this will be x an element of, and it will have to be 0 to infinity. But just to fix here quickly, I'll need a round bracket at the 0, and a round bracket at infinity as well. The reason I need a round bracket is because x won't actually get to 0, because the y-axis or the line x is equal to 0 will be my asymptote. Right. So let's carry on and have a look at the rest of our questions. Now they say, g, so this is this guy over here that I'm blocking off. G is now reflected in the x-axis to give me a graph H. Right. Now, we've spoken last week and earlier today about what happens if we reflect in the x and the y-axis. If I reflect in the y-axis, x becomes negative. If I reflect in the x-axis, y becomes negative. So, now I need to give the equation of this line. So basically what I'm doing is I'm putting a minus in on the left-hand side here. But because we want our graph on the form y equals, the minus now goes there. So that's minus log to the base 2 of x. Right, so we just keep on reflecting our graph. Now, next question asks me, find the value of h of 1. Okay, now what that means is in the place of x, what I need to do is I need to replace the x with a 1. So I need to find the value of log to the base 2 of 1. Now I know what the answer is, but particularly because we haven't sketched the graphs, this is where our calculator comes in really handy. And let's do our whole calculator. I'm going to say f of x is equal, and I'm going to do that. I want to put a minus in front. I don't know actually how I'm going to do that. Okay, but I'm going to put a 2 over there and a 1 over there. Oops. Dungy, it's not my lucky day today. F of x is minus, let's do it like that, and log to the base 2, scrolling along to 1 equals. Okay, now start at minus 4, that's fine, end, it's fine, step 1. The main thing that I'm looking for now is I want to see what is the y value at x equal to 1. So I'm just going to scroll down. And at x equal to 1, the y value is 0. Now, guys, you can learn for yourself that the log of 1, it doesn't matter what its base is. It absolutely doesn't matter what its base is. The log of 1 will always be 0. But I've just shown it to you guys now by using the table function on my calculator. Right, let's have a look at the next question. The next question says, find the value of x if h of x is equal to 2. Now, I'm going to leave the calculator out of this now. I'm going to say, right, h of x is minus log to the base 2 of x. And basically, I'm now going to say minus log to the base 2 of x is equal to 2. Right. So that's what I'm going to do. And now putting this, what I'm going to do is I'm just going to take the minus back to the top. I'm allowed to do that. So log to the base 2 of x to the power minus 1 is equal to 2. Now, if I put this from log form into exponential form, I get that x to the power minus 1 is 2 to the power 2. Now, we've spoken about log in exponential form before. So x to the minus 1 is 4. So basically, 1 over x is 4 over 1. And then cross multiplying and solving for x, there are easier ways to get there. X is equal to a quarter. So basically, in the last two questions, what they did is they gave us an x value, they asked us for the y. So they gave us an input, they asked us for the output, and then they did the opposite. They gave us the output, and they asked us for the input. Right, so I hope that you guys are following. Looney, any questions, comments, or suggestions from the page, or is everybody managing to follow quite okay?
Yes, Yash is asking, says, I face some problems on finding the gradient.
On finding the gradient.
Yes.
That's not really applicable now with functions. What she might be referring to is more calculus, where you have to get the derivative and substituting in the x value to find the gradient. But in this particular section, boys and girls, we're not really dealing with the gradient much.
Okay.
Right.
And then Gerbert is asking, what do you mean by a restricted domain?
Okay. What do I mean by restricted domain? That is a very good question. What I mean by that is, usually, for an exponential graph, the graph is drawn for x an element of r. In other words, it goes all the way to negative infinity and all the way up to positive infinity. But in this question in particular, they told me it's only drawn from minus 2 to 3. So they gave me the restriction. Right? If they write nothing, then there is no restriction. But if they specifically give you a restriction on the domain, then you must use that restriction on the domain. And remember that the restriction on the domain in the original graph will be the x and the y will swap around for the inverse. So the restriction on the domain is very much something that they have to give you. They've got to put it there in brackets.
Okay.
Right, so can we move on to our next question, do you think?
Yes.
Okay. They say to us, consider the functions f of x is equal to 2 to the power 2 times x squared, and g of x is a half to the power x. Now, this over here, what we're dealing with here is a parabola. Now, we're definitely going to do more of these sorts of questions next week. This graph over here is an exponential. Now, guys, my feeling is always, regardless of whether I'm asked to draw the graph or not, when I read the question, I have a mental picture of what the graph looks like. The same way if you read a book, you've got a mental picture of what your hero looks like. My heroes are parabolas and exponential graphs, so I like to know what they look like. If I look at f of x equal to 2x squared, that is a parabola. It will be symmetric around the y-axis, and it'll look something like this. It'll turn there at 0, 0. Okay? Now, the exact steepness you won't know, but if you have no idea what the graph looks like, remember to use the table function on your calculator. So this is f of x equal to 2x squared. Fine. Now, over here, I've got an exponential graph, and the a part, the base, is a half. And we have learned tonight, or I've taught you, I don't know whether you've learned, that if I've got a fraction there between 0 and 1, my graph is decreasing. Right, so it's going to look something like that. Fine. And that is g of x, and that is a half to the power x. Fine. Put a bracket there. Let's have a look at our questions. So the questions make a lot more sense if you know what you're talking about. That's really, really important. So the question says to me firstly, restrict the domain of f so that the inverse of f will also be a function. Right. Now, because we haven't really done this before, this is more a teaser for next week. I'm going to draw the inverse of f for you guys. Remember, inverses are symmetrical about the line y is equal to x. So if I were to draw this graph's inverse, it's going to look a little bit something like that. Okay, like the purple graph. Now, the original graph, my green graph, was a function because it passed the vertical line test. However, if I now hold my ruler over the purple graph, I can see that it intersects in 2 places. So therefore, the inverse is not a function. Now, they say I must restrict the domain of f so that the inverse is also a function. Now, do you guys agree with me? If one of these halves, of these purple halves, weren't here, then the inverse would still be a function. So let's have a look. If my original graph looked like that only, then its inverse would look like that, and the original graph and its inverse would be a function. Similarly, if my original graph only had that leg, like that, over there, then the inverse would be something like that. Okay. So basically, what do I need to see here is, as long as I've got both arms of my parabola, its inverse will fail the vertical line test, so its inverse won't be a function. So I now need to give an instruction to make the original graph only half of the graph. Now, I said to you guys earlier that this parabola will turn at 0, 0. So I've got 2 choices. I can either restrict the domain to only the negative x values, and I'm talking about the restriction on the domain is now the original graph. So I can say x an element of negative infinity to 0. Then my original graph will only have that arm, and its inverse will only have that arm. That's my one option. You get one of two options. Alternatively, I could go to this option where only the positive arm is drawn, so the inverse will be also only one arm, and this is then x, an element of 0 to infinity. Right, but guys, more about that next week. But the point is, if you have a parabola, which is a one-to-many function, its inverse won't be a function. So you've got to take away either the one side of the parabola or the other side in order to make its inverse still a function. Right. Just quickly, let's have a look at the next part of the question. They haven't, I just want to see here quickly, we haven't actually really been asked anything about the exponential graph. But anyway, the exponential graph, its inverse will still be a function. All right. The next question says, the inverse, restrict the domain of f so that the inverse is also a function, and then that should be a and this should be b. B says, write the inverse of g in the form g to the minus 1x equals. Now, this is what I taught you guys earlier tonight. This will be, its inverse will be log to the base of half of x. So remember, if the original is y is equal to a to the power x, its inverse will be log to the base a of x. So there I've answered that question. Fine. Then there's yet another question, question C. And question C says the inverse of a function is 2x minus 4. Give the equation of the original function. So guys, to move from a function and its inverse interchangeably, if my inverse is 2x minus 4, how did I get to 2x minus 4 from the original graph? By swapping the x and the y around. So I'm going to say, okay, my inverse is 2x minus 4. But to get back to the original graph, I'm going to swap the x and the y around. So I'm going to say x is equal to 2y minus 4. And remember what I said to you guys earlier on in the program. It's considered really ugly to write your answer not in the form y equals. So I'm going to do that. Bring the 4 over. And then y is a half x plus 2. And what you'll see in this one, if you swap x and y around, you'll get to this one and vice versa. Looney, time flies when you're having fun.
Yes.
I can't believe it's time to say goodbye already, and we've got a whole other question.
Guys, all good things have to come to an end. Thank you so much for welcoming us into your homes, for commenting on the Facebook page, for tweeting us, everything that you needed to do throughout the show. Guys, it's been amazing. It's been great. Thank you so much for tuning in. And I'd just like to remind you guys that you can download all the show notes, the schedules, and the videos on our learnextra.co.za/live page. So you can do all that, guys, during the holidays, during the week, during the weekend. You can always go through that page, guys, and you see what you need to get from the information that you're given on that page. Thank you so much for joining us, guys. And until next week, same time, same place.
Good night.
Good night, guys.